Alright, this is AP Chem 1.3 homework. I'll be going over problems 92, 103, and the AP Chem FRQ. 92 is just asking you for the chemical formula, the empirical formula, so the most simplified formula from the percentages of each atom. For each element. So this might look very confusing, but there's a very easy way to unpack this, and this method you'll use often from now on. Well, I wouldn't say often, maybe 3 times on the AP exam, so it's important to know this. You're going to convert these percents into grams. So you could either do what I did, where I said 100% is 1 gram, so then 77.87% is 0.7787 grams. Or you could say 77.87 grams, so saying 100% is 100 grams, although that might be a little more math than you might want to do. But anyway, for example, I did 0.7787 grams carbon, 0.1176 grams hydrogen, blah, 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 blah. So from there, we're going to want to convert to moles because your empirical formula is going to be given in moles. So I divided by moles, and I got these numbers that you'll see on the screen. And then in order to get your formula, you're going to divide by the thing you have the least of. And now, you might be wondering, why are we doing that? Well, in order to get our empirical formula, we have to kind of establish all of these relative to each other, kind of like how we did that for limiting reagents yesterday. So we're going to divide by the thing we have the least of, so that, for example, we know that the thing we have the least of is oxygen here. So if you divide the amount of oxygen by itself, you get 1, and then if you divide like 0.006, if you divide 0.116 by that value, you'll get a larger value, and you get a larger value for carbon as well. So you'll get your empirical formula. And just the formula is C10H18O1. So that is the empirical formula because you're dividing by the smallest thing, so that you could have the smallest whole number. Because if you were to divide by hydrogen, which it could still work, it would not give you your empirical formula. It would give you a fraction for oxygen, of probably a fraction for carbon as well. Same thing if you divided by the carbon value, you would get a fraction. And you may be wondering, why are we doing this? Why are we dividing? Well, it's in order to set these relative to each other, and it's in order to get a formula so you have these kind of at whole numbers like that. And also, it was like 10.004. You can just say 10 to round up. I don't remember exactly what it was, but you round up or round down. Anyway, a mass spectrum of eucalyptol shows a peak at about 154 atomic mass units. What is the molecular formula of the substance? So, if you want to do the math, I won't. I googled it. C10H18O is 154 atomic mass units. The molar mass of it is 154. Therefore, the mass spectrum of eucalyptol and this empirical formula, matches. Therefore, the molecular formula matches the empirical formula. So the molecular formula is also C10H18O. And the difference between the empirical formula, again, the empirical formula and the molecular formula, is that the molecular formula often has, for example, like a molecular formula could be like C2O18 and H4. That could be the molecular formula. That could be the actual structure of the molecule. However, if you wanted the empirical formula, that would be just getting the most simplified lowest whole number you could have. So the empirical formula could be C09H2. That would be the empirical formula. So that's the main difference. But since these match, the empirical formula matches the molecular formula. So there's no worries. Anyways, next problem. Alright, 103. So this is just saying that when a mixture of acetylene and oxygen reacts, it makes water and carbon dioxide. And it's asking you what is the balanced chemical equation, and what is the limiting reactant, and how much is left after this reaction happens. So hopefully the easiest part for you was the balancing. So it already gives you all of the chemicals. The only thing you need to do is balance. If this was hard for you, or it took you like a very long amount of time, I recommend finding a better method or perfecting or using more practice problems, because balancing is a very important part of the AP exam. So I really recommend you do some practice or find a new method. I have a video out on that. But if you didn't have any problems, you don't have to worry about that. Anyway, for part B, which is the limiting reactant? So in this problem, I use a different method. I converted the grams of acetylene to grams of oxygen, and based off of that, I found which one I had more of. If I had more grams of acetylene, like the converted acetylene to oxygen, for example, in this problem, I converted the grams of acetylene to grams where, like, through stoichiometry, you cross out grams, you cross out moles of acetylene, and then you cross out. I just basically converted to grams. I found that I had more grams of oxygen than I did than I had grams of the real oxygen. So I found that oxygen was a living reactant, not acetylene, because I converted acetylene into oxygen just so I could compare them in an easier way for me, at least for me. So I found that oxygen was a living reactant. All right. And then for part C, how many grams of C2H2, O2, CO2, and H2O are present after the reaction is complete? I will write out all the work for that problem, and I will go over that in just a second. Okay, so I'm using the teacher's handbook for this aspect of the problem because there was a lot of writing, and my writing just did not fit on the screen, so yeah. Anyway, so obviously, for the first part, we know that there are no grams of oxygen left because all of the oxygen has been consumed in the reaction because that's the thing you have the least of. And you will have some acetylene left over. So the first thing I did, and the first thing the textbook did, was find the amount of acetylene remaining. So what you're going to want to do is convert your grams of oxygen to grams of acetylene through stoichiometry. I can go over this really quickly. You cancel out grams through molar mass, and then you cancel out moles of oxygen, and then you cancel out moles of acetylene, and you're left with grams of acetylene. And we find that 3.26 grams of acetylene are consumed. Then you're going to want to subtract that from the amount of acetylene left. At first, so you do 10 grams minus 3.26, and then you would find that you have 6.7 grams of acetylene remaining. And that is the first part. Well, I guess the second part of our problem solved. Now we're going to want to do the products. Now, the products, and someone asked me about this before, why are there different amounts of products being produced? It's because, especially in this problem, you need twice as much carbon to match this amount of water because a 4:2 ratio, 1:2 ratio, every 2 moles of carbon dioxide means 1 mole of water. So you're going to be producing more carbon dioxide compared to water, or you're going to need more carbon dioxide compared to water. So that's why in our answers we have different amounts of carbon dioxide and different amounts of water. So in order to find the amounts produced, you're just going to convert your grams of oxygen to grams of carbon dioxide and grams of hydrogen water respectively. So just simple stoichiometry again, you're going to want to cancel oxygen, cancel moles of oxygen, and then find grams of both carbon dioxide and water respectively. And you find 11 grams of CO2 and 2.25 grams of H2O. The reason why you have a different amount, again, is because you have different ratios. You have a 4:5 here, and you have a 2:5 here. And you also have different molar masses, so you have different amounts of grams. All right, that's all for the textbook problems. Onto the AP FRQ. Okay, so this is the AP FRQ. This is going to be kind of long, but I'll try to make this quick. So this is just describing a reaction, but without giving you anything that happened. But water is added to this chemical, and then the products are this solid and this gas. And part A is asking, determine the formula of the gas. So do what I did in problem, I don't remember the number, but the first problem. You convert percent to grams, so 0.95 grams of fluorine, 0.05 grams of hydrogen, and then you divide by molar mass to convert to moles, and you will get, and the thing is with this is that you'll get the same number or very, very close. I rounded all my molar masses, so it's the same, but if you got the exact, you get something slightly different. However, if you round, you will still get 0.05 and 0.05. Therefore, it's a 1-to-1 ratio. So you'll have for your empirical formula, you'll have 1 mole of hydrogen to 1 mole of fluorine. Therefore, your empirical formula is hydrofluoric acid. And that is the empirical formula of the gas. All right, next problem, I'll write it out. Okay, what fraction of the fluorine of the original compound is in the solid and what fraction is in the gas? So this is going to be using a new concept. basically I'm going to be converting my grams to moles. That's the first thing. Obviously, that's the first thing you do. And then we're going to do something kind of weird. We're going to be multiplying or dividing, depends on what you're doing, by the amount of moles of the atom or element that you have in that compound to get the amount of grams, or the amount of moles or grams of whatever atom you're looking for. So, for example, in this first problem, I found the moles of UF6, or uranium fluoride, and then I multiplied by 6 moles of fluorine, because there are 6 moles of fluorine in this molecule. So in 1 mole of uranium fluoride, there are 6 moles of fluorine. This is kind of like a chemical equation, except you're only doing it in a formula. It still works though. And with that, I get 0.0 blah 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 moles of fluorine. And I do the same with hydrofluoric acid, and I get 0.0485 moles of fluorine. And then from there, I'm going to divide 0.0485 divided by 0.07273, and I got 66.6%, but it's like 2/3 of the fluorine. What was it? Yeah, of the fluorine was in the gas, and therefore 33% was in the solid. All right, time for part C. Okay, so I'm going to go over part C and D. So, what is the formula of the solid product? This is probably the most strenuous part of the problem. So, we're going to be taking things from 3 different answers. So, first of all, let's start. So, how do we get this formula? Well, first we need the moles so you know how in prior problems we used the percentage to find, so I said like 33% was carbon, 66% was fluorine, or something like that, and you just used the method I showed you. We're going to do it the same way, but without the percent, and using different methods of getting it. So, so we're going to need to get all of the things. We're going to need to get all the moles of what we need in our formula, which is what? Uranium, oxygen, and fluorine. So let's start with uranium. So the uranium in the reaction comes from uranium fluoride. So we're going to want to convert for uranium. So like I did in part B, we're going to find the moles of uranium through just stoichiometry. So 4.267, and then divide by molar mass. And then this is a 1-to-1 ratio. There's 1 mole of uranium and 1 mole of uranium fluoride. It's a pretty straightforward calculation, so you'll get 0.01212 moles of uranium. And then from part B, it kind of crossed out. We find that it is 0.02433 moles of fluorine, because we know that 33% of the fluorine was in the solid, based off of my answer in part B, and 33% is this amount. So yeah, we know that. And then finally, for the water, we are just going to do the same method. We're going to find our moles, and then we use our conversion. We know that there's 1 mole of oxygen and 1 mole of water, so it's still going to be a pretty straightforward reaction. Straightforward calculation, and we will get 0.02406 moles of oxygen. And now I'm going to use the method that we used last time, where you divide by your least amount so that you get the lowest whole number the lowest whole number factors. Because if you divided by like the middle value or the highest value, you'll get fractions. It would still be the correct formula, don't get me wrong, but you'll get fractions, and it won't be empirical. And it won't be like readable. It'll be really strange to look at. So we're going to divide by our lowest amount, which is uranium, and we will get the formula UF2O2, because uranium divided by itself is 1, and then there are about 2 moles of fluorine and about 2 moles of oxygen. So we get this final answer. And I understand that this is kind of difficult, so if you need more explanation on this, I can go over it in Discord or in call or whatever. And then for part D, the final part, write the balanced equation between UF6 and H2O, assuming blah blah blah. You already know everything, like you already know all the formulas, so all you need to do is just balance. Oh, and this is 4HF, sorry. 4HF, that cut out. So you'll get 1 mole of uranium fluoride, 2 moles of water, 1 mole of UF2O2, and you'll get 4 moles of hydrogen fluoride. And that's all. Have a good night. And for some of you taking the 8-push test, good luck with the 8-push test. And for some of you getting your SAT scores like me, good luck to you too. All right, see ya.